Voyager 2 is still moving, but it is no longer going anywhere. Tonight, I want to walk you through the strange life of a machine that is still moving, faster than almost anything humans have ever built, and yet is no longer going anywhere. Voyager 2 was built to do a job, and it finished that job in 1989. Everything since then is a postscript. The spacecraft is still moving outward at 15 kilometers per second, but the universe it is moving through has no destination for it. It is not aimed at any star. It will never arrive at anything in any meaningful sense. It is just continuing. By the end of tonight, you will understand the difference between moving and going somewhere, and why those two things, on the scale of a galaxy, are not the same. Now, let's begin. There's a particular kind of clean room at the Jet Propulsion Laboratory in Pasadena, California, where the spacecraft we now call Voyager 2 was assembled in the years before its launch. The room had filtered air, soft fluorescent light, and a small group of engineers who, depending on the week, were either ahead of schedule or panicking. The spacecraft sitting on its assembly stand looked, to anyone who walked in, like a bus with a giant dish antenna bolted to the top and a long boom of scientific instruments pointing off the side. It weighed about 825 kilograms. It was about the size of a compact car. It carried 10 primary scientific instruments and a small library of cassette tape data storage that, by today's standards, you would describe as charmingly insufficient. What was not is the thing most people imagine when they hear the word Voyager. It was not built to be the farthest human-made object from Earth. It was not built to cross into interstellar space. It was not built to send back data from beyond the heliopause. It was not built to carry a message to other civilizations. And it was not built to outlast the careers of the people who made it. Those things are real. Those things are happening. But they are not what was on the design specification. What was on the design specification was something much simpler. Voyager 2 was built to fly past Jupiter and Saturn, and possibly Uranus and Neptune if the budget held and the spacecraft survived. It was built to take photographs of those planets and their moons, measure their magnetic fields, sample the charged particles around them, and send all of that data home. The mission, as specified, was supposed to last about 5 years, with a possible extension to 12 if everything went well. After that, the spacecraft would essentially become a ghost. A working spacecraft, perhaps, but one with no remaining mission to perform. A piece of hardware drifting through empty space, with nothing left to do. If you had asked any of the engineers in that clean room in 1976 what would happen to Voyager 2 40 years later, the honest answer was that nobody really expected to find out. The radio link would probably weaken before then. The instruments would probably fail. The plutonium power source would probably decay below the threshold of usable electricity. The spacecraft would still be moving, of course, because in space nothing slows you down, but it would be moving silent and dark, sending nothing, hearing nothing, doing nothing. The original mission ended at Neptune. Everything after Neptune was, from the engineering perspective, gravy. That fact is the entire foundation of the story I want to tell you tonight. The version of Voyager 2 that has captured the public imagination, the romantic interstellar pilgrim, the silver disk with a golden record, the tiny machine drifting toward the stars, carrying greetings from Earth, is a kind of accidental afterlife. It is the second life of a machine that completed its first life 37 years ago and has been quietly running on borrowed time ever since. And here's the part that I think gets glossed over in almost every story about this spacecraft. Voyager 2 was never sent toward anything. It was not aimed at a star. It was not pointed at a destination. The golden record attached to its side, the famous message we are sometimes told the spacecraft is carrying to other civilizations, was attached to a machine that was launched through a temporary alignment of the planets and then left to drift. There is no civilization at the end of its path. There is no star at the end of its path. There is no end of its path. The spacecraft is moving very fast, in a direction that has no destination. That is the heart of the story. Hold that thought. We're going to keep coming back to it. To understand why Voyager 2 was built, you have to understand a quirk of orbital geometry that only repeats itself once every 176 years. In the late 1960s, a young engineer at JPL named Gary Flandreau was working through trajectory calculations for hypothetical outer solar system missions. He noticed something. In the late 1970s, the four giant outer planets, Jupiter, Saturn, Uranus, and Neptune, were going to line up in a particular kind of arrangement, with each one positioned in such a way that a spacecraft could use the gravity of the previous planet to slingshot itself toward the next. This is called a gravity assist. You arrive at a planet, fall into its gravitational pull, swing around it, and leave with more speed than you came in with, headed in a new direction, for free. The fuel you would otherwise need is provided by the planet itself. The alignment Flandreau identified meant that a single spacecraft, with a relatively modest amount of fuel, could in principle visit all four of the giant outer planets in one continuous trajectory. The catch was that the launch window opened around 1977 and would not open again until 2153. If you missed it, your great-grandchildren would have to take the trip instead. That is the alignment Voyager 2 was built for. It is the only reason the spacecraft has the trajectory it does. It is the only reason its scientific objectives extended all the way out to Neptune. The 1977 launch date was not chosen because it was a nice round number or because the engineering was finally ready. It was chosen because the planets themselves had set a deadline, and missing the deadline meant losing the chance entirely. There would not be another opportunity until 2153, by which time the engineers who had identified the alignment would be long dead, and the political and economic context that had made the program possible would have shifted in ways nobody could predict. The mission had to fly in 1977, or it would not fly for another 6 generations. Voyager 2 launched on August 20th, 1977, from Cape Canaveral, Florida. Its twin, Voyager 1, launched 2 weeks later on September 5th. Despite the names, Voyager 2 went first. Voyager 1 was launched on a faster, shorter trajectory specifically designed to reach Saturn and its moon Titan before Voyager 2 got there. Voyager 1 was the priority. Voyager 2 was the backup, the slower probe that would only continue to Uranus and Neptune if Voyager 1 succeeded at Saturn. That is the origin of one of the small ironies of the Voyager program. Voyager 2 was built as a fallback. Its long mission, the one that took it past 4 planets and eventually out into interstellar space, was made possible because Voyager 1 succeeded at the harder, more time-sensitive Saturn flyby and freed Voyager 2 to keep going. The spacecraft you have probably heard the most about, the one we are talking about tonight, the one that has gone the strangest places, is the one that almost got asked to do something else entirely. Step the camera back, and the whole picture is one of geometry. Voyager 2 exists because the planets were briefly in the right places, and someone noticed. It was built for a journey the universe had outlined, and then would not offer again for almost 2 centuries. The mission Voyager 2 was actually built for has a name. It is called the Grand Tour, and it lasted, in its complete form, from August 1977 to August 1989. 12 years and a few weeks, planet to planet, with quiet stretches of cruising in between. That window, those 12 years, is the entire reason the spacecraft exists. Everything you have ever heard about Voyager 2 doing science in the heliopause or sending back interstellar data is happening on a machine whose actual job ended on August 25th, 1989. Let me walk you through what the Grand Tour actually involved, because I think it gets glossed over in the rush to talk about interstellar space. In July 1979, Voyager 2 reached Jupiter. It came within about 645,000 kilometers of the cloud tops. It returned the first detailed images of Jupiter's faint ring system. It returned the first images of active volcanoes anywhere besides Earth, on the moon Io. Until that moment, every textbook description of volcanism had been a description of one planet, our planet. Voyager 2 quietly added a second one. It also gave the first hints of the ocean beneath Europa's icy crust. In August 1981, Voyager 2 reached Saturn. The rings turned out to be far more structured than anyone had predicted. Where ground-based telescopes had shown a few broad bands, Voyager 2 showed thousands of narrow ringlets, gaps, and braided structures that should not, by any simple model, have existed at all. After Saturn, Voyager 1's planetary mission was essentially complete. Voyager 2 was kept on the original trajectory, the one that would, with the right gravity assists, take it to 2 more planets nobody had ever seen up close. In January 1986, Voyager 2 reached Uranus. This was the first close-up visit any spacecraft had ever made to that planet, and it remains the only one. The planet rotates on its side, with its axis pointed almost directly at the Sun, and Voyager 2 was our only close look at what that does to a planetary system. Miranda, one of its moons, was covered in cliffs and grooves that looked like a planet that had been broken apart and reassembled. In August 1989, Voyager 2 reached Neptune. Again, the only close visit any spacecraft has ever made. It came within about 4,950 kilometers of Neptune's cloud tops, the closest approach to any planet on the entire mission. The moon Triton turned out to be one of the strangest objects in the solar system. It has active geysers. It orbits Neptune in the wrong direction, against the planet's rotation. Its surface is covered in ice unlike anything we had seen before. Triton remains the only direct look we have ever had at a Kuiper Belt object up close. That was the mission. 12 years, 4 planets, dozens of moons, and an enormous body of scientific data that fundamentally changed our understanding of the outer solar system. Every objective on the original list was completed. Every instrument was used. Every photograph that had been planned was taken. When Voyager 2 left Neptune in late August of 1989, the mission, as specified in the documents in that JPL clean room 13 years earlier, was complete. There was no plan for what came next. There was no defined Phase 2. The spacecraft was going to keep moving, because nothing was going to stop it. But the engineering and scientific team that had built it had already done what they had set out to do. That is the moment the story turns. Everything you have ever heard about Voyager 2, the interstellar pilgrim, the message to the stars, the spacecraft that crossed the boundary of the solar system, all of it happens after this moment. All of it happens to a machine whose actual job is already finished. If Voyager 2 had simply gone silent at that point, every contractual and scientific obligation would have been honored. But it did not go silent. The instruments were still working. The radio link was still strong. The plutonium was still warm enough to keep producing power. So the team in Pasadena did the natural human thing. They asked the question that always gets asked at the end of a successful project that has not actually broken yet. They asked, what now? What we now call the Voyager Interstellar Mission, or VM, was approved in 1990. It was not part of the original program. It was a kind of bureaucratic improvisation, a recognition that the spacecraft was still healthy, still in contact, still capable of returning useful science, and that turning it off and walking away from it would be a waste. The mission, as it was now redefined, was very simple. Voyager 2 would keep flying, on whatever trajectory the Neptune flyby had given it, and it would send back data on whatever it encountered along the way. There would be no more planetary flybys. There were no more planets in the spacecraft's path. The new mission was about the space between things. The thin gas of the outer solar system, the magnetic fields, the charged particles streaming out from the Sun, the eventual boundary where the influence of our star gives way to the influence of the rest of the galaxy. This is the version of Voyager 2 that has captured the public imagination. The interstellar pilgrim, the little machine sailing out into the dark, sending back postcards from places no instrument had ever been. It is a romantic image, and it is also true. But it is important to understand that this version of Voyager 2 is the second life of a spacecraft that was never designed for it. Most of the instruments that survived past Neptune were the ones that had been built to study planetary magnetic fields and charged particle environments. The cameras, the imaging spectrometer, the photopolarimeter, those were planetary instruments. They were designed to look at planets. There were no planets left to look at. So in 1990, after Voyager 2 took a final image of the planets behind it, and after Voyager 1 took a similar final image, the cameras were turned off to save power. The software that controlled them was eventually removed from the spacecraft entirely. The ground systems that processed the camera data were retired. The engineers who knew how to operate them moved on to other missions, retired, and in some cases, passed away. The cameras on Voyager 2 are still physically attached to the spacecraft, but in every meaningful sense, they are gone. Even if we wanted to turn them back on, we no longer have the means. What was left were the instruments that could study a less visible world. The magnetometer, which measures magnetic fields. The plasma science instrument, which measures the density and direction of the thin ionized gas around the spacecraft. The cosmic ray subsystem, which counts high-energy particles from the galaxy. The low-energy charged particles instrument, which measures the slower particles streaming out from the sun and from interstellar space. The plasma wave instrument, which listens, in a sense, to the electrical disturbances rippling through the medium the spacecraft is moving through. These were the instruments that carried Voyager 2 into its second life. They were not built for what they ended up doing. They were built to study planetary magnetospheres, the bubble-like magnetic environments around the giant planets. But planetary magnetospheres turn out to share a lot of physics with the much larger heliosphere, the bubble of solar wind that surrounds our entire solar system. And so the same instruments could be repurposed to study the heliosphere from the inside. For the next 30 years, that is what Voyager 2 did. It moved slowly through the outer reaches of the heliosphere, sending back data on what was around it. It crossed the termination shock, the point where the supersonic solar wind slows down, in 2007. It crossed the heliopause, the actual boundary of the solar system in the most precise sense, in November 2018. It is now in interstellar space, but it is doing all of this on borrowed instruments, with no plan, on power that diminishes by 4 watts every year. And what it found, the moment it crossed that boundary, was nothing the engineers in Pasadena had been expecting. The crossing of the heliopause in November 2018 is one of the genuinely strange moments in the history of space exploration. Strange because the data we got back did not match the models. The boundary was not what scientists had thought it would be. Let me explain what the heliopause actually is, because the word gets used a lot without much definition. Our sun produces a constant stream of charged particles, a kind of wind made of plasma, called the solar wind. The solar wind blows outward in every direction, filling a roughly spherical region around the sun with this hot, fast-moving plasma. That region is called the heliosphere. It is, in a real sense, the bubble of our home star's influence, the volume of space where solar wind dominates over the much thinner gas between the stars. The heliopause is the outer wall of that bubble. It is where the solar wind slows down to a stop, balanced against the pressure of the interstellar medium pushing back against it. Before Voyager, we had no direct measurements of where exactly that boundary was, what it looked like up close, or how thick it was. We had models and educated guesses. The models predicted a fairly smooth, gradual transition. The plasma density should rise as you cross the boundary. The magnetic field should change direction in a predictable way. The temperature of the surrounding medium should follow a particular curve. Voyager 2 crossed the heliopause on November 5, 2018, at a distance of about 119 astronomical units from the Sun, which is roughly 17.8 billion kilometers. The data it sent back over the following weeks and months was different from what the models had predicted in several specific ways. The plasma density just outside the heliopause was higher than expected, not by a small amount. The interstellar medium right outside our solar system is denser than the models said it should be. We had assumed for decades that the heliosphere was pushing outward against a thin, mostly empty surrounding gas, and that the boundary between them was a relatively quiet transition. What Voyager 2 found instead suggested that the medium just outside our solar bubble is being compressed in some way, perhaps because of the motion of the entire solar system through the interstellar gas, perhaps because of structures in the local neighborhood we have not yet mapped. The detection has been independently confirmed by Voyager 1, which crossed its own piece of the heliopause 6 years earlier in 2012. Both spacecraft, in different parts of the boundary, found a denser interstellar medium than the predictions. That is not a small finding. That is a fact that will reshape models of how stars interact with their galactic environments for decades to come. The magnetic field on the interstellar side of the heliopause did not behave the way the simulations had said it would. The transition was sharper. There were fluctuations and structure that the smooth models had not captured. There were pressure fronts moving through what was supposed to be empty space, ripples in the medium that the spacecraft could feel as small electrical disturbances picked up by its instruments. Some of those pressure fronts are believed to be the remnants of solar storms that had erupted on the Sun years earlier and were still propagating outward, well beyond the heliopause, slowly dissipating into the interstellar medium. Voyager 2 was, in effect, listening to the long-delayed echoes of solar weather, the parts of the storm that were still moving long after the original storm itself had ended. Nobody had predicted, in any precise way, that the spacecraft would be able to do this. We discovered, in short, that the boundary of our solar system is not a smooth wall. It is a turbulent, structured, surprisingly busy region of space, and it does not match what theorists had spent decades modeling. The data from Voyager 2 forced revisions of basic ideas about how the heliosphere interacts with the rest of the galaxy. This is the kind of discovery that justifies a mission. This is the kind of return that makes a spacecraft worth keeping alive. This is the reason the engineers at JPL have spent the last 30 years carefully managing the slowly diminishing power supply, turning off heaters, deactivating instruments, finding clever ways to extend the life of a machine that has nothing left to lose. But it is also a reminder, the instruments that made these measurements are not infinite. They are not even durable. They are the same instruments that flew past Jupiter in 1979 and Saturn in 1981 and Neptune in 1989, and they are now nearly half a century old. They are running on a nuclear power source whose fuel is decaying. They are being kept alive by engineering tricks that by a year here and a year there, we caught the heliopause crossing in time. We are still receiving data, but the window is closing, and it is closing faster than people realize. The power source on Voyager 2 is called a radioisotope thermoelectric generator. It sounds complicated, but the principle is simple. You take a quantity of plutonium, an isotope called plutonium-238, and you let it decay naturally. The decay produces heat. You wrap that heat-producing core in a structure that converts the heat into electricity, using a kind of thermoelectric effect, and you wire that electricity into the spacecraft. This is how Voyager 2 has been powered for 48 years. It has no solar panels. It is too far from the sun for solar panels to be useful. The sun, at 13 billion miles, is just another bright star. Plutonium decay is the only practical option for a spacecraft going where Voyager 2 was going. The problem is that plutonium decay is, by definition, a process of running down. Every year, there is a little less plutonium in the core, because some of it has decayed into other elements. Every year, the heat output is a little lower. Every year, the electricity available to run the spacecraft is a little less. The decline is steady. It is roughly linear over the timescales we're dealing with. It works out to about 4 watts of lost power per year. 4 watts is not very much. It is less than the power consumption of a smartphone charger. But on a spacecraft that started with about 470 watts of total electrical power and has now lost a substantial fraction of that, 4 watts a year matters enormously. The team at JPL has been managing this slow decline for decades. They have been making decisions about which subsystems to keep running and which to turn off. They have been turning off heaters, accepting that some parts of the spacecraft will get colder than they were designed for, in exchange for keeping science instruments alive. There is a careful balance involved. If a heater is turned off and the part of a spacecraft it was warming gets cold enough, electronics can stop working, fuel lines can freeze and crack, mechanical systems can seize. But if a heater is left running, that is power that cannot go to a science instrument. Every choice is a trade-off. Every trade-off is irreversible at distances of tens of billions of kilometers. Some of these decisions have been small. Some have been large. All of them have been irreversible, or nearly so. Once an instrument is shut down on a spacecraft 13 billion miles away, the practical reality is that it stays shut down. You can send a command to turn it back on, but the command takes nearly a day to get there, and you have no real way to verify whether the instrument will respond. In most cases, the team has chosen not to take the risk. An instrument that is off is at least predictable. An instrument that is partially broken can fail in ways you cannot anticipate. And on a spacecraft this old, every failure is potentially terminal. So the slow shutting down of Voyager 2 has been going on for years. Most of it has been quiet. A heater here, a subsystem there. Nothing that made the news. Nothing that the public would have noticed. But in the last 2 years, the shutdowns have started reaching the science instruments themselves. And that is a different kind of milestone. This is where the spacecraft stopped quietly aging in the background and started visibly dying. In October 2024, the team at JPL turned off the plasma science instrument on Voyager 2. This is the instrument that had been measuring the density and direction of the plasma in interstellar space. The same instrument that had detected the unexpectedly dense medium just outside the heliopause. The decision was made because the instrument's orientation relative to the direction of plasma flow had degraded over the years, and it was returning limited data anyway. But the underlying truth is that the team needed the power. Every watt that goes to a marginally useful instrument is a watt that cannot go to a heater somewhere else on the spacecraft. And heaters matter, because if a part of the spacecraft gets cold enough, fuel lines can freeze, electronics can become unreliable, and small mechanical components can fail in ways that have nothing to do with electricity at all. In March 2025, the team turned off the low-energy charged particles instrument on Voyager 2. This is the one that measured the slower charged particles streaming through the interstellar medium. It had been operating almost continuously since the spacecraft's launch in August 1977. It had been running for 47.5 years. By the time it was deactivated, the small motor that rotated its viewing platform had completed more than 8.5 million steps. It had been originally tested to 500,000. Let me say that again, because the numbers deserve attention. The motor was designed to last through 500,000 steps. By the time NASA finally shut it down, it had completed 8.5 million. It outlasted its design specification by a factor of 17. That is the kind of margin that does not happen by accident. That is the kind of margin that happens because the people who built that motor in the 1970s were so cautious, so conservative, so unwilling to accept any risk of failure, that the device they built could run, in a sense, forever. These are not small losses. The plasma science instrument and the low-energy charged particles instrument were two of the spacecraft's most scientifically valuable remaining instruments. They were measuring things that no other spacecraft has ever measured, and that no other spacecraft will be in a position to measure for many decades, possibly ever. Then, on April 17, 2026, just over 2 weeks before tonight's recording, the team turned off the same instrument, the low-energy charged particles instrument, on Voyager 1. Voyager 1 is Voyager 2's twin, the older sibling, the one that crossed the heliopause first in 2012. It is now 25 billion kilometers from Earth. It takes about 23 hours for a command to reach it. On February 27, 2026, Voyager 1's power levels dropped unexpectedly during a planned roll maneuver. Any further drop in power could have triggered the spacecraft's automatic undervoltage fault protection system, which would have shut down components on its own to keep the spacecraft from dying entirely. That kind of automatic shutdown is much harder to recover from than a planned one. The mission team needed to act first, deliberately, before the spacecraft was forced to act for them. So they sent a command to turn off the low-energy charged particles instrument. The command took 23 hours to reach Voyager 1. The instrument is now dark. Voyager 1 has 2 remaining functional science instruments, a magnetometer and a plasma wave subsystem. The mission engineers expect this shutdown will buy the spacecraft about a year of additional operation before the next instrument has to be turned off. The reason I am telling you about Voyager 1 in a video about Voyager 2 is because the same thing is about to happen to Voyager 2, in a slightly different form, in the next 2 months. The team at JPL has been planning what they call the Big Bang maneuver for both spacecraft. The idea is simple in principle, complicated in execution. Instead of turning off science instruments, the team will swap out a group of power devices all at once, replacing some with lower power alternatives, to keep the spacecraft warm enough to continue gathering science data while reducing total power consumption. It is the engineering equivalent of replacing the heaviest furniture in a house with lighter versions of the same furniture, all in a single afternoon, on the chance that the floor underneath will hold the new arrangement long enough for someone to live there. They're going to try it on Voyager 2 first. Voyager 2 has slightly more power to spare and is closer to Earth, so the round-trip command time is shorter. If something goes wrong, the team has a slightly better chance of catching it and reacting before the spacecraft crosses some threshold from which it cannot return. The tests are scheduled for May and June of 2026. By the time you are watching this, that work is either underway or about to begin. If the Big Bang maneuver succeeds, both spacecraft may be able to continue operating with at least one science instrument into the early 2030s. That is the most optimistic version. The realistic version is that, instrument by instrument, year by year, Voyager 2 is going dark. The data we are still receiving from interstellar space is data we will not be receiving for very much longer. There is no replacement coming. There is no other spacecraft anywhere near where Voyager 2 is. There will not be another spacecraft anywhere near where Voyager 2 is for many decades, possibly a century or more. The science we are losing is not science we are going to recover anytime soon. And if you are asking yourself, well, at least the spacecraft itself will keep going. At least it is on its way somewhere. At least there is still that. I have to tell you something honest about what those words actually mean. I want to pause here for a moment and talk about a phrase. The phrase is halfway home, and you may have seen it used to describe Voyager 2 in various places. It is a comforting phrase. It suggests progress. It suggests that the spacecraft is somewhere along a journey, that it has covered a meaningful fraction of the distance, that it is on its way somewhere it will eventually arrive. I want to be honest with you. The phrase is a kind of lie. Voyager 2 is still moving, but it is no longer going anywhere. There is no halfway home, because there is no home it is going to. The spacecraft is not headed for a destination. It is not aimed at a specific star. It is moving in a direction, and that direction happens to take it through certain regions of space and past certain stars at certain distances, but none of that constitutes arrival. The spacecraft will pass close to a small star called Ross 248 in roughly 40,000 years, and we will get to that in a moment. But close, in this context, means about 1.7 light-years, which is roughly 16 trillion kilometers, which is to say, not close at all by any standard a planetary scientist would recognize. Voyager 2 is moving at about 15.34 kilometers per second relative to the Sun. At that speed, it covers about 3.1 astronomical units every year, where 1 astronomical unit is the distance from the Earth to the Sun. The nearest star system, Alpha Centauri, is about 277,000 astronomical units away. At Voyager 2 speed, ignoring all other factors, reaching Alpha Centauri would take roughly 89,000 years. But Voyager 2 is not headed toward Alpha Centauri. The phrase halfway home is the kind of phrase that gets used in headlines and infographics, and it captures a real fact, which is that Voyager 2 has been flying for 49 years and could potentially keep flying for several thousand more years before any instrument has any chance of being read by anyone. But halfway implies a midpoint, and a midpoint implies an endpoint, and there is no endpoint here. What there is instead is a kind of slow drifting through a galaxy that is itself moving. The Sun orbits the center of the Milky Way once every 225 to 250 million years. It carries the entire solar system with it as it orbits. The nearby stars are also orbiting the galactic center on slightly different paths, at slightly different speeds. Voyager 2, when it eventually passes beyond the Sun's gravitational influence, will join that same kind of orbit. It will become, in effect, another small object orbiting the galactic center on its own independent path. It will keep moving for as long as the galaxy keeps existing. That is not halfway home. That is not on the way somewhere. That is just motion. The spacecraft will keep moving, but motion through interstellar space, in any honest description, is not the same thing as travel. It is not the same thing as journey. It is just continuing. The reason I am being careful about this language is because I think the language matters. The language of arrival, of destination, of journey, is the language we use for things that have endings. Voyager 2 does not have an ending in any meaningful sense. It has a long, slow continuation. The romance of the interstellar pilgrim is built on a kind of misunderstanding about what motion through space means at these distances and on these timescales. We have a habit of imagining the spacecraft as something like a ship at sea, slowly making its way across a known body of water toward a known shore. The reality is closer to a leaf falling from a tree. The leaf is moving. The leaf is going somewhere. But there is no shore, and there is no destination, and after enough time has passed, the leaf is just somewhere on the ground, indistinguishable from any other leaf that has fallen from any other tree. Hold this thought too. We're going to come back to it. In about 40,000 years, Voyager 2 will pass within 1.7 light-years of a small red dwarf star called Ross 248. The star is in the constellation of Andromeda. It has about 12% the mass of the Sun and about 16% the radius. It is a flare star, which means it occasionally brightens unpredictably as the result of magnetic activity. As far as we know, it has no planets, although the absence of evidence is not the same as evidence of absence. Ross 248 is itself moving. It is currently about 10.3 light-years from the Sun, but its motion through the galaxy is bringing it closer to us. In about 36,000 years, Ross 248 will become the closest star to the Sun, briefly displacing the Alpha Centauri system from that title. It will come within about 3.02 light-years of us. Then, as the geometry continues to shift, it will move away again. The encounter between Voyager 2 and Ross 248 happens, in a sense, by accident. Voyager 2 is not aimed at Ross 248. Ross 248 is not aimed at Voyager 2. The two trajectories happen to bring the spacecraft and the star within 1.7 light-years of each other, around the same time, and that is the closest the spacecraft will ever come to any star other than the Sun. I want you to feel what 1.7 light-years actually is. A light-year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. In a year, that works out to about 9.46 trillion kilometers. So 1.7 light-years is about 16 trillion kilometers. Compare that to the distance between Earth and the Sun, which is about 150 million kilometers. The closest approach between Voyager 2 and Ross 248 will be roughly 107,000 times the distance from the Earth to the Sun. Compare that to Pluto's average distance from the Sun, which is about 5.9 billion kilometers. The Voyager 2 to Ross 248 closest approach will be roughly 2,700 times the distance from the Sun to Pluto. Compare it to Voyager 2's current position. Voyager 2 is currently about 21.35 billion kilometers from Earth. The 1.7 light-year missed distance is about 750 times Voyager 2's current distance from Earth. If you imagine the entire 49-year journey Voyager 2 has already made, the closest approach to Ross 248 will still be 750 times further away from the star than Voyager 2 is currently from us. The spacecraft will fly for another 40,000 years to come within 750 times its present distance of any star. That is the geometry. That is the actual closeness we are talking about. Or compare it to the speed of light. Light from Ross 248, at the moment of closest approach, will take about 1 year and 8 months to reach Voyager 2. If something on Ross 248 emitted a signal at the moment of closest approach, the spacecraft would not detect anything from the star for over 20 months. By the time the signal arrived, the spacecraft would have moved another 40 billion kilometers further along its trajectory. The two objects are moving in slightly different directions, at slightly different speeds, and the universe between them, even at closest approach, is large enough that light itself takes a meaningful fraction of a human lifetime to cross it. This is not a flyby. This is not even a flying year. This is a mutual passage through approximately the same region of the galaxy, on timescales and at distances that have no analog in any human experience. If you were standing on a hypothetical planet around Ross 248 with the best telescope you could imagine, and you knew exactly when and where to look, you might be able to see Voyager 2 as a point of reflected starlight, briefly, before it moved on. You would see no signal from it. You would receive no transmission. You would have no way to know what it was, where it had come from, or what it carried. It would just be a small, dark, silent object moving through your sky, far enough away that your telescope would barely resolve it as anything more than a glint. And by then, Voyager 2 will have been silent for 39,980 years. There is a famous object attached to the side of Voyager 2. It is also attached to Voyager 1. It is called the Golden Record. It is a gold-plated copper disc, about 30 centimeters across, encoded with sounds and images from Earth. It contains greetings in 55 languages. It contains music, including pieces by Bach, Beethoven, Chuck Berry, and traditional songs from many cultures. It contains the sound of waves, of thunder, of birds, of a kiss, of a mother and a child, of laughter. It contains 116 images encoded as analog signals that, in principle, can be reconstructed if you have the right equipment. The record is housed inside an aluminum cover that has, etched on its outside, a series of diagrams explaining how to play the record, where Earth is located in the galaxy, and what kind of star our sun is. The golden record is one of the most beautiful objects humanity has ever made. It was assembled under the guidance of Carl Sagan and a small team of collaborators, with the explicit purpose of being a message from Earth to whoever, or whatever, might find it. I want you to sit with the actual mathematics of that purpose for a moment. The Voyager spacecraft are moving through a region of space that is, by any measure, almost completely empty. The density of stars in our part of the galaxy is so low that the average distance between stars is roughly 4 light-years. The probability that a randomly drifting object will encounter any star, in any close way, over any reasonable amount of time, is vanishingly small. Astronomers have done the calculation. The expected timescale for a Voyager spacecraft to actually collide with, or be gravitationally captured by, another star is on the order of 10 to the 20 power years. That is 1 followed by 20 zeros. It is many, many times the current age of the universe. The golden record was made, in part, as a message, but it was also made as a kind of human gesture, a way of saying that we existed, and that we cared enough about our own existence to send a small piece of evidence about it out into the dark. The probability that anyone or anything will ever play the record is, in honest scientific terms, indistinguishable from zero. The team that made the record knew this. Carl Sagan, in his writings about the project, was very clear that the record was unlikely to ever be found by any external civilization. The point of the record, for Sagan and the others involved, was not really the message itself. The point was the act of making it. The point was the choice to put together a portrait of Earth, in 1977, with the resources we had, the knowledge we had, the cultural priorities we had, and to attach it to a spacecraft that was, for the first time in human history, going to leave the solar system permanently. The record is, in that sense, more a self-portrait than a letter. The record will outlast the spacecraft. The record will outlast the sun. The record will outlast the human species. The record is, by some calculations, the most durable artifact our civilization has ever made. The aluminum cover and the gold plating will protect it from cosmic ray damage for billions of years, as long as it is not destroyed by some specific event, like a collision with another object or a close passage through a star. The golden record will continue to exist, in the form it was made, for timescales that exceed the lifetimes of most galaxies. By the time the sun expands into a red giant in 5 billion years and swallows the inner planets, Voyager 2 will still be drifting somewhere in the galaxy, with the record still attached, still etched, still potentially playable if anyone could ever find it and figure out how. By the time the Milky Way collides with the Andromeda Galaxy in about 4.5 billion years, the record will still be there, somewhere, on its long path, through whatever the merged galaxy becomes. It will exist. It will not, in any reasonable scenario, be played. That is the part of the Voyager story that I find genuinely strange. The most ambitious message humanity has ever attempted to send into the universe is, in practice, a message we sent to ourselves. The golden record is more important as a symbol of what humans do than as a functional communication. The actual probability that an alien civilization will encounter the spacecraft, recognize it as artificial, decode the diagrams on the cover, build a player for the record, and listen to its contents is, for all practical purposes, zero. This does not make the gesture meaningless. I want to be clear about that. The gesture is meaningful precisely because we made it. The golden record is not a failure as a message. It is a success as an act of imagination. It is a record of who we were when we built it, and it will continue to be that record long after the people who built it are gone. But it is not going to be played. It will not be found. Whatever Voyager 2 was built to find, in the most expansive possible interpretation of that phrase, the golden record was the message we wanted it to deliver, and that delivery is, by any honest reckoning of probabilities, never going to happen. This is the second sense in which Voyager 2 will never make contact with what it was built to find. The Deep Space Network is the system of large radio antennas located in California, Spain, and Australia that NASA uses to communicate with spacecraft beyond Earth orbit. It is the only system on the planet capable of receiving the very faint signals that come back from the Voyager spacecraft. The signals from Voyager 2, by the time they reach Earth, are about 20 billion times weaker than the signal from a typical mobile phone. The Deep Space Network amplifies and decodes these signals using extremely sensitive equipment that has been upgraded over the years specifically to keep up with the slow weakening of the Voyager signal. There are antennas in the network that have been continuously listening to the Voyager spacecraft in shifts for almost half a century. The window during which the Deep Space Network can continue to receive useful data from Voyager 2 is closing. NASA estimates that the spacecraft will remain within range in terms of signal strength and remaining instrument operation until around 2036. After that, even if the spacecraft is still warm enough to function, the signal will be too weak to extract meaningful data, and the remaining instruments may have been turned off long before then. There may come a year, sometime in the next decade, when the team in Pasadena makes a final decision to stop trying to listen because there is nothing left to hear, or because the cost of the antenna time outweighs the diminishing return of whatever weak signal might still be coming through. So the actual functional life of Voyager 2 is now measured in years, not decades. We are looking at perhaps another 10 years of useful science return, and that is on the optimistic end. After that, the spacecraft will continue to exist and continue to move and continue to drift, but it will be silent. It will not be sending data. It will not be observing anything. It will be a piece of inert hardware on a long, empty trajectory. When that signal cuts off, whether by gradual fading or by deliberate shutdown, it will end one of the longest continuous data streams in the history of science. Voyager 2 has been transmitting data, almost without interruption, since August 1977. There are very few human projects of any kind that have run that long. There are almost none in the history of space exploration. When the signal ends, we will not be replacing it. There's no Voyager 3. There's no plan for a follow-on interstellar mission within the timescale that any current engineer's career will overlap with. The few mission concepts that have been proposed for interstellar probes would not, even if approved tomorrow, reach the heliopause for several decades. Voyager 2 is not the first of a series. It is the only one of its kind, and it is going quiet. The space between stars will become, once again, a region we know about only through models and theories. The direct measurements will stop. The pressure fronts and density variations and magnetic fluctuations that Voyager 2 has been quietly mapping will go back to being things we infer rather than things we observe. There will be a kind of darkness about the data, a place in our understanding of the universe where we used to have a single, faint, unbroken thread of measurements coming back from a real spacecraft in a real region of space, and now we will only have the memory of those measurements and whatever we have already learned from them. This is what I mean when I say Voyager 2 will never make contact with anything it was built to find. The contact, in the literal sense of two-way communication, ends in this decade. After that, the spacecraft is on its own. It will keep moving. It will pass close to Ross 248 in 40,000 years. It will pass somewhere near Sirius in nearly 300,000 years. It will eventually settle into a long, slow, independent orbit around the center of the galaxy, traveling in its own path, completing one orbit every couple of 100 million years, for as long as the galaxy itself continues to hold together. There will be no further messages. There will be no further data. The spacecraft will be there, and that is all. Halfway home, in any meaningful sense, is not a place Voyager 2 is heading. It is not a place that exists. Let me describe, as carefully as I can, what happens to Voyager 2 in the very long run. The spacecraft is currently moving outward from the Sun at about 15 kilometers per second. It is heading roughly in the direction of the constellations Sagittarius and Pavo, about 48 degrees below the plane of the planets. It is still, technically, moving away from the Sun, but the Sun's gravity continues to pull on it, very weakly, and that pull continues to slow the spacecraft down very slightly. Eventually, after enough time has passed, the spacecraft will reach what is called escape velocity threshold relative to the Sun. From that point onward, the The sun's gravity will no longer be the dominant force on its motion. What replaces the sun's gravity as the dominant force is the gravitational pull of the rest of the Milky Way galaxy. The galaxy is not a uniform thing. It has structure. It has spiral arms, denser regions, dust clouds, individual stars. As Voyager 2 moves through the structure, its path will be perturbed in small ways by the gravitational influence of whatever it passes near. It might pass close to a wandering rogue planet, an object in interstellar space, without a star of its own. There may be more such rogue planets than there are stars. We do not know. If Voyager 2 happens to pass close to one, its trajectory will shift slightly. Over millions of years, many such small shifts will accumulate, and the spacecraft's path will become impossible to predict in any detail. The 40,000-year prediction for Ross 248 is reasonably accurate because that is a short enough span that the geometry of the local neighborhood is well known. The hundreds of thousands of years prediction for Sirius is rougher. Anything beyond about 1,000,000 years is essentially guesswork. The further out you go in time, the wider the cone of possible trajectories becomes, until the spacecraft could be almost anywhere in the local part of the galaxy. But the overall pattern is clear. Voyager 2, like every other object in the galactic disk, will end up in a long, slow orbit around the center of the Milky Way. The center of the Milky Way is about 26,000 light-years away from Earth. The Sun completes one orbit around it every 225 to 250 million years. Voyager 2 will join the same kind of orbit, on its own slightly different path, and will continue to orbit, again and again, for as long as the galaxy itself remains gravitationally bound. The spacecraft, in this very long sense, will become a small additional member of the local stellar neighborhood. Not a star, not a planet, not anything that produces or reflects significant light, but a small dark object on its own quiet orbit, in the same general population as everything else in the disk. Estimates of how long that is depend on assumptions about dark matter, the eventual collision of the Milky Way with the Andromeda Galaxy in about 4.5 billion years, and various other large-scale processes. But the simple version is that Voyager 2, barring some specific destructive event, will continue to exist and to orbit for billions of years. The probability that it will collide with any star over those billions of years has been estimated at around 1 in 10 to the 20th power, which is to say, effectively zero. So this is the long picture. Voyager 2 was built to fly past 4 planets in 12 years. It did. Then it was repurposed to fly outward from the solar system, into the heliopause, into interstellar space, sending back data on a region of space we had never directly studied. It did that too. Now it is winding down, instrument by instrument, year by year, and within the next decade it will go silent, and after it goes silent it will continue to drift, slowly losing the memory of where it came from, until it joins the population of objects that orbit the center of the galaxy on their own quiet paths. And in roughly 40,000 years, somewhere along that very long orbit, it will pass close enough to Ross 248 that, on a galactic map, the two paths will cross in a region of space that astronomers might mark with a small notation. They will not be in contact with each other. There will be no signal. There will be no observation. There will be no exchange of any kind. There will just be two objects, briefly close, in a galaxy where briefly is measured in millennia. That is the closest Voyager 2 will ever come to anything. Stillness is an illusion, even in the most empty places we can think of, even in the spaces between stars, where the density of matter is so low that you could move for centuries without encountering anything. There is still motion. There is still drift. There are still things falling, in the long sense of the word, toward the center of the galaxy. Voyager 2 is part of that motion now. It has crossed over from being a spacecraft on a mission into being a small object on an orbit, an object that no longer has anywhere to go because there was never anywhere to go, only the going itself. We were not wrong about Voyager 2. We were wrong about what it meant to send something. The spacecraft has done what it was built to do, and a great deal more that no one expected. The science it has returned has changed our understanding of the boundary of our solar system, of the structure of interstellar space, of the medium that lies between the stars. It has been one of the most successful scientific missions of any era, and it is winding down in front of us. The lesson, I think, is not about failure. Voyager 2 has not failed at anything. The lesson is about what arrival means, and what motion means, and how the scale of the universe changes the meaning of those words. The spacecraft is still moving. It will be moving long after every person currently alive has died, long after the last person who remembers it has died, long after the species that built it has either become something else or stopped being a species at all. The spacecraft will keep moving, but moving and going somewhere are not the same thing. The next time you hear someone say that Voyager 2 is on its way to the stars, remember that the phrase is doing some quiet work. The spacecraft is moving in a direction. It is not going to a destination. It is part of the slow turning of the galaxy now, on a path that will outlast every person currently alive, and probably every person who will ever be alive, and possibly the species itself. It will keep moving. The golden record will keep existing. The aluminum cover will keep its etched diagrams. And nobody will ever play it, because nobody will ever find it, because that is the kind of universe we live in. The 48 years of operation, the 4 planets it studied, the boundary it crossed, the data it returned, all of that is in the past now. The remaining decade of useful science is the last chapter of a story that started in 1977 and is now, slowly and quietly, ending. The spacecraft itself will continue. It will be there, somewhere, for billions of years. It will pass close to stars, occasionally, on the kind of timescale that makes the word close almost meaningless. It will carry the record we attach to it. It will not, in any honest sense, do anything else. Halfway home was always a lie. There was no home it was going to. There is only the going, the long quiet drifting of something we made, that we built carefully, that we send off with the best instructions we could put on the side of an aluminum case, into a darkness that has no edge. Voyager 2 is still moving. It is no longer going anywhere. How incredible is that? Good night.